Hi, Gen Bio. Hope you guys are all doing well. Today we are going to talk about diffusion and osmosis. So diffusion is the movement, the spreading out of particles over an area of space. Okay, this is a passive process, and it's due to the fact that molecules have a type of energy called thermal motion. So they just randomly move. It's associated with their temperature. So an increase in temperature increases the speed at which the molecules move, and a decrease in temperature slows down that movement. But the net result is that if you have an area of space that a molecule can spread out over, it will over time, okay? And once this happens, we say that it's reached equilibrium. There's no confinement of the particles in one area, so it's spread out and it's at a steady state. Okay, so let's move to the next slide. The key factor when there is an unequal distribution of particles is that there will be a concentration gradient. So there's going to be more particles on one side than the other. And this implies that there's going to be a barrier in between that's keeping the movement of particles separate and the two spaces distinct. So when there are more particles on one side and less particles on the other side, then we call this a concentration gradient. So there's more on one side, less on the other. And in biology, one of the major barriers that would create this unequal distribution is, of course, a cell membrane. We're keeping some things out of the cell and some things in the cell. Okay, if a particle is able to cross that barrier, whatever it be, the cell membrane or artificial barrier, it will to achieve equilibrium, and it will move in the direction from where it has a higher concentration to where it has a lower concentration. So if you look at the picture in the PowerPoint here, you'll see that there's an artificial barrier in my container here, this red dotted line, and there are more particles on one side and less on the other. And when these particles move, if they're able to cross that barrier, they're going to move from the side where they have a higher concentration to the side where they have the lower concentration. And this we say as the substance diffusing down its concentration gradient, okay? And again, this is a passive process. No energy is required for this to happen, okay? So of course, the cell membrane is going to be our focus for the barrier between things that are inside and outside of the cell, okay? The cell membrane has a wonderful ability to regulate what comes into or out of the cell, and this is a controlled process. It's selectively permeable, which means that it allows some things to come across and other things to not pass, depending on what the cell needs or does not need to operate, okay? So one of the large molecules, one of the, I should say, most important molecules that needs to be regulated is water. So aquaporins are special channels that are shown in the picture here. This yellow structure here is an aquaporin. It allows water to be moved from one side of the cell to the other. And it happens quickly, but it is regulated based on the concentrations of particles inside or outside of the cell, okay? So these little red and white molecules, these are water, and as you can see, they're passing into or out of the cell through the aquaporin. And then the blue here is our lipid bilayer, our cell membrane, okay? So we've got a tight regulation of things going across. It can be water or it could be other things. Ions in particular often have channels that allow them to cross or not into or out of the cell. Larger molecules will not pass as readily as smaller molecules, and depending on the charge and other factors, they may or may not be able to get into the membrane at all. Okay, let's move to our next slide. So osmosis is a particular type of diffusion, and it's specifically the diffusion of water, okay? As water crosses the membrane, it will also move from an area where water is more highly concentrated to where water has a lower concentration, okay? Now this can be affected though, not just by the prevalence of water molecules, but by the prevalence of other particles in solution. So if you look at the picture here, you can see that there are more particles on the left side of my container than on the right side, okay? If these particles could cross the membrane, they would go from left to right to even out that concentration gradient. But sometimes we have what's called non-penetrating particles. So the solutes, because of size or charge or regulation by the cell membrane, if the solutes cannot cross the membrane, the semi-permeable barrier, then what might happen to even out the concentration gradient is that water would move in the reverse direction to, again, equalize the concentration gradient. So if you've got more water over here and less over here, so more on the right, less water on the left, then water would be moving from right to left in this container, okay? So this equates basically to movement from the low solute concentration, the low particle concentration, to the higher solute concentration, so higher number of particles. But water would be the thing moving if the particles can't cross the membrane, okay? Okay, next slide. So osmolarity or osmotic pressure, these are terms that we use to refer to solute concentration in a solution. So osmolarity is very similar to molarity. It's a measure of concentration, but it is different in that it's affected by the number of particles that a molecule forms in solution. So some things, when they're placed in solution, they have the ability to dissociate. For instance, sodium chloride. Sodium chloride is made up of sodium and chloride, and when it's not in solution, that's one particle of sodium chloride. However, when placed in water, then sodium and chloride dissociate, and now they form two different particles. So this is a quality associated often with ionic compounds. They can dissociate in water. This is not true of all particles. So for instance, glucose and sucrose, sugars, they do not break down in solution. So if you look here, a 0.2 molar solution of glucose, since it doesn't dissociate, it's going to have an osmolarity of 0.2 osmoles per liter, okay, same, 0.2 molar, 0.2 osmoles per liter, okay? This changes, again, when the particle dissociates when placed in water. So if we're talking about sodium chloride, a 0.2 molar solution of sodium chloride is actually going to have an osmolarity of 0.4 osmoles per liter. And the way that you would calculate this is that osmolarity is equal to the molarity times the number of particles that the molecule forms in solution, okay? So since sodium chloride dissociates into two separate particles when placed in water, then you would have the molarity, 0.2 molar, multiplied by 2. So of course, then we get 0.4 osmoles per liter, okay? All right, moving to our next slide. We have some terms that describe two different solutions that we're comparing to each other. So the first one is isosmotic. Isosmotic is a description for a solution that has the same osmolarity as the other solution that it's being compared to. So if we had equal numbers of particles on the left and the right and equal amounts of water, then those two solutions would be isosmotic, okay? The second term is hypoosmotic. So hypo, if you think about that prefix, it means less, right? Hypo, as opposed to hyper, which would mean more. So hypoosmotic is the description for a solution that has a lower osmolarity, so less particles than the solution to which it's being compared. So if you look at our picture, the solution with the lower number, fewer number of particles is the one on the right. So if you're comparing it to the solution on the left, you would describe the solution on the right as being hypoosmotic, less particles, okay? And the reverse would be true for the hyperosmotic term. So there's more particles, a higher osmolarity in this solution on our left in our picture. So it's going to be hyperosmotic. It has a higher osmolarity, more particles dissolved, okay, compared to the solution on the right. Okay, I hope that all makes sense. I'm going to add a couple more terms specifically that describe the situation where you have particles that cannot cross the barrier. They can't cross that semi-permeable membrane. So osmolarity, which we just discussed, refers to solutions that have both particles that can and cannot cross the membrane. So we call them penetrating and non-penetrating particles. The other term that kind of goes hand in hand with this and is very similar is tonicity. The difference is that tonicity refers to solutions that have non-penetrating particles, so they cannot cross that barrier. And so what will happen, as we discussed a few slides back, is that then water will move to even out the concentration gradient. And how this affects our cells is that the volume of the cell can be altered. Water can move out of the cell, water can move into the cell, okay, through the aquaporins. And as that happens, then the volume of the cell is altered. And this, again, is referred to as tonicity when we have specifically non-penetrating particles. So the terms below here are very similar to those on the previous slide. Isotonic refers to a solution that when it's surrounding the cell is not going to change the cell volume because the concentrations are relatively equal in the cell and outside of the cell. Okay. A hypotonic solution then is the description for a solution that surrounds the cell, which, now remember, hypo will mean less, so there are less particles outside. Hypotonic, if we're talking about the hypotonic solution being outside the cell, there'll be less particles outside. And what that means then is that proportionately there's more water, right? And so the water will move into the cell, and this causes the cell to swell because it's increasing in its volume. It can then become very rigid if it's, for instance, a plant cell and it has a cell wall. It'll swell and it'll push that volume up against the cell wall and become rigid or turgid. If, on the other hand, it's an animal cell and there is no cell wall, then what can happen actually is if it swells too much, then the cell can actually burst because there's no cell wall to maintain that pressure and maintain the structure of the cell. Okay, so that's when the cell is in a hypotonic environment and is taking up water from the external environment, from the extracellular space. All right, and then the last term here is hypertonic. If we're talking about a solution that is surrounding a cell being hypertonic, it means there's more solutes outside the cell, and therefore we're going to see a loss of volume from the cell as water moves from the cell into the extracellular environment, okay? And this causes the cell to decrease in volume, and it can shrink, it can do what we call plasmolyze. And I will move to the next slide to show you a picture of these, okay? So these pictures, the top 3 pictures are red blood cells. Of course, these are animal. These are going to be our example of animal cells. The bottom 3 pictures are our examples of plant cells. And these are placed in isotonic solutions on the left, hypotonic solutions in the middle, and hypertonic solutions on the right-hand side of this picture, okay? So again, if they're in isotonic solutions, you've got no real change in direction, no net change in the flow of water from one direction to the next. Now, if you look at the hypotonic solution, then the cells are in a hypotonic solution. So outside of the cell, in the extracellular environment, there are less particles. And so water will be moving into the cell. And in an animal cell, again, that causes swelling, potentially bursting, which we call cytolysis. In a plant cell, then it just pushes that cell membrane up against the cell wall, and this we refer to as turgidity, a pressure or a rigidity placed on that cell wall because of the swelling due to increase in volume, okay? And then in our hypertonic solution, when there are more particles outside of the cell volume will decrease, water will be moving out of the cell, and so you're seeing this shriveling here due to the loss of water from inside our red blood cells. And then in our plant cell, you still have that cell wall, but you're seeing the cell membrane pull away from the cell wall, actually shrivel a little bit. Because again, we've lost water from inside our cell to the extracellular environment, okay? And so this is when the cell membrane pulls away from the cell wall, we might see some wilting shown here in our plant cells. You can see if a plant does not get enough water, you can see that loss of rigidity of the cells, which then allows the whole plant to droop and lose its structure, okay? And this we call plasmolysis of our cells, okay? All right, next slide. Temperature has an effect on this. It's not an effect on the direction of water movement. However, it is an effect on the speed at which the water may move into or out of the cell. So heat, as I mentioned earlier, speeds up the molecule's movement. It doesn't affect the direction. You're still going to see the influx or efflux of water based on tonicity, but you will see that process happen quicker when you apply heat to the cell. If the cell is placed in a colder environment, then the opposite will happen. The movement of the molecules will slow down, and you won't see that change happen as rapidly, okay? There's an exception to this that I want to point out. If the solution is heated so much that it can actually degrade the proteins, then you can have damage to your aquaporins. So those channels that allow water to pass into and out of the cell, again, those were called aquaporins. If they have been in too hot of an environment, then they can be affected such that their structure deteriorates and they are not able to allow water to pass from one side to the other of the cell. And so you might not see the same directional change of water movement because of the damage to the aquaporins. So if you heat it too much, then you might not observe this effect of temperature on the movement of our molecules, okay? All right, next slide. So our goals for this week's lab, we are going to be looking at the gain or loss of water weight based on the environment that we're placing cells into. And we're going to use potato cores as our plant cells. They obviously have cells in them. We're going to cut out pieces of the potato and put them into different concentrations of either sodium chloride or sucrose. And some of you will be doing one, some of you will be doing sodium chloride, and some of you will be doing sucrose. So then we'll compare data afterwards. And again, we're going to observe the water weight change in our potatoes over time when they're in a different concentrations of sodium chloride or sucrose. So if it's in a really high concentration of sodium chloride, you're going to have lots and lots of particles in that extracellular environment, lots of solutes. And so what you would expect to see then is that water movement will happen from inside the potato cells to outside. Water would move out to even out that concentration gradient. Okay, we're going to observe this and see if that happens over the course of an hour and 15 minutes, 75 minutes if possible. And then we're also going to look at the effective temperature. Hopefully we'll see that by placing the potatoes into a warmer environment, that this process happens more rapidly, because that is what we expect to happen. And then the last thing that we want to do, well, a couple things we want to do, is determine the osmotic point of potatoes. So the point at which they are not gaining or losing any water. And then we can record the molarity, the osmolarity of the solution that we place the potatoes in, where the potatoes do not gain or lose weight. So that would be the isosmotic point of our potato cells. Okay. All right, now I want to put one clarifying slide in here. We're not going to actually record, well, we're not going to graph the actual weight change of the potatoes. In lieu of doing so, we are going to record and graph the percent weight change. So we're going to have you weigh your potatoes beforehand and weigh them at each step along the process. But at the end, we want to actually graph the percent weight change, because this gives a more accurate picture. For instance, for example, you can report that a person lost 10 pounds. Now, if the person started at 100 pounds and they lost 10 pounds and now they're 90 pounds, then that's one story. That's one piece of information. However, if you have a different person who started at 300 pounds and they lost 10 pounds, that's a very different story in terms of percent weight change. So if you were to do the calculations, the way to do this is to start with your weight at time t, which for us is going to be the last time point, or each time point along our process. So say at 75 minutes, an hour and 15 minutes, we take that weight of the potatoes and subtract from it the weight at the start of our experiment, okay, for the potatoes. And then divide it by the weight, again, at the starting point, at time 0. Multiply by 100, that'll get us our percent weight change. So for instance, just to drill this point home a little bit more, for the 100-pound person that I described, if they lost 10 pounds, they've lost 10% of their body weight, which is a significant amount, more significant, I would say, than the 300-pound person who now weighs 290 pounds and started at 300 pounds. So they lost a little over 3% of their body weight. So these are two different stories that are more accurately told by giving the percent weight change instead of the actual weight change. You'd say they both lost 10 pounds, but it shows a more clear picture by doing the percent weight change. So that's what we're going to have you do, calculate and graph the percent weight change of our potatoes from the starting point to the ending point of our experiment. All right, let's move to the next slide. Practically speaking, for lab this week, you're going to start by cutting out potatoes. We have little cork borers, little drill apparatuses that you will use to cut out pieces of potato, weigh them, and then you're going to place them into solutions of either sucrose or sodium chloride. And these solutions will vary in concentration. You're going to weigh your potatoes every 15 minutes for 75 minutes, and then record and graph whether or not the potatoes gain or lose weight in each of the different concentrations. So of course, bringing this back to our theory, this is due to osmosis. The movement of water is what's actually causing the change in weight of our potatoes, okay? So we're also going to look at the effect of temperature. We're going to keep the temperature study all in the same concentration. So it's going to be 0.75 molar for our hot temperature, which is going to be 40 degrees, our room temperature, which is going to be 23 degrees, and our cold, which is 4 degrees Celsius, okay? All of that's going to be the same concentration. To keep that variable the same, the temperature will be the only thing that changes for that part of the experiment. All right, and then there's some questions that are really good for you to work through in your lab manual that will help you process what you think should be happening and what is actually happening. So you should answer those. And then there's going to be 3 graphs that you do for this week's lab. The first graph is the percent weight change for the different concentrations of sodium chloride or sucrose, so over time. Okay, the second graph is going to show the effective temperature, and the third graph will show the percent weight change of each of the concentrations at the 75-minute mark, so the final time point. And this will allow us to determine 2 things: the isoosmotic point of potatoes and the concentration of a solution that I'm going to give you that you do not know the concentration of, so the unknown. All right, so I have examples of each of those 3 graphs here for you to use as a reference. So the first one, again, we are looking at the percent weight change of potatoes over time. So on our x-axis, we've got time in minutes, and on our y-axis, we've got the percent weight change of the potato cores, okay? Some of our potatoes will gain weight. Some of them will lose weight, and this is going to be dependent on the osmolarity of the solution that they were placed in, okay? So again, if there's more particles outside of that potato, more solutes in the solution, it's going to lose weight because water will be moving out of the potato into the extracellular environment. There's more particles if it's a hypertonic solution. If it's a hypotonic solution, so less solutes outside, then you're going to see water movement into the potato, and then it will gain weight. So what you should see then, what you should be able to create at the end of our experiment is a graph that looks a lot like this then, where you see some of our potatoes that were placed in different concentrations will be gaining weight. Some of the potatoes will be losing weight, again, dependent on the osmolarity of the solution. So that's the first graph. The second graph is the percent weight change of our potatoes in different concentrations of our sodium chloride after, now it says here 90 minutes, but for you guys it's going to be 75 minutes because we have to cut everything a little bit shorter. So percent weight change of potatoes after 90 minutes, and you might be doing sodium chloride or you might be doing sucrose, dependent on which group you're going to be placed in, okay? So each of these data points indicates whether or not the potato core lost or gained weight. And what you should see is that with an increase in concentration, this is the concentration on our x-axis, with an increase in concentration of the surrounding environment, you're going to have more water moving out of the cell. So weight, the potato weight will go down. If you have less solute concentration outside, so a hypoosmotic or hypotonic environment outside of the potatoes, then you're going to have more movement of water into the potato cells and then an increase, a positive percent weight change, okay? Increase in weight. All right, and then the last graph that you will do is the effective temperature. You're going to look at a single concentration. So it's going to be the 0.75 molar concentration of sodium chloride or sucrose. And you're going to place those potatoes into different temperatures. So a 4 degree, a 23 degree, and a 40 degree. And again, what you should see, because you're using the same concentration, they should all of your lines should be moving in the same direction. The concentration is what determines the directionality of water movement. It's only speed that should be changing. So in a warmer environment, you should see that movement happen quicker. And as you can see, in this graph, hopefully you'll get similar results, is that the hot temperature, the 40 degree, you do see that drop in weight earlier. And then in our room temperature, it happens quicker than at our cold temperature. Okay, so you should see something like that. And if we let it go long enough, you should see that the actual change in movement should level off, okay, after it goes long enough, but that it happens quicker in a warmer environment. All right, so that is all I have for today. I will see you shortly, and if you have any questions, you can always email me at cfry@lvc.edu. Thanks a lot, and see you soon.